All right, let's look at an example of a harder problem. So let's imagine a rod, a 1 meter rod. Only this rod has non-uniform density. In other words, the mass is not consistent throughout the whole rod. So we're saying this is 1 meter long. And let's just say that for any little sliver, we can find the mass at that little sliver, a position x away. So what we're going to say is that the density, which is a little change in mass over the change in length, which is, we'll say, change in x, our density at any point equals x. So, for example, at this little section, we'll say like 0.3 meters away, the density of this little sliver, the density of that little sliver is 0.3. And the little mass of that sliver then, d mass, would be our density, 0.3, times the distance, dx. And this gets us our general statement that a little bit of mass for this particular problem, so this is just like a specific, an example problem. Example. So for this example problem, that's a 1 meter rod with a density that depends on x, what we would know is that our a little change in mass is equal to x dx. Okay, so this is all some leading up to the idea of finding the center of mass. So we know that the center of mass is 1 over the mass times the integral of x dm. Well, since we're talking about x, what we need to do is change dm to something in terms of x. So we get x center of mass equals 1 over mass times, x times x dx. And we're going from 0 to 1. Okay, well, before proceeding with the integral, we need to find the mass. Well, how are we going to find the mass? The mass simply is the sum of all the little masses. So and the sum of all the little masses, so the integral of dm is the same as the integral of x dx from 0 to 1. And so that's just going to be 1/2 x squared, integrating that from 0 to 1, which is just 1/2. So that's the mass of my rod. So going back to finding the center of mass is 1 over the mass, which we just found the mass is 1/2. So we could replace this with just 2. That was the integral from 0 to 1 of x squared dx. So doing a little bit of integration, we get that the x center of mass equals 2 times 1/3 x cubed from 0 to 1, which simplifies to 2/3. And this makes sense because as we move from left to right on our rod, it's getting heavier and heavier and heavier. So it makes sense that the center of mass is going to be to the right of our midpoint of the rod. And so our center of mass is occurring here at around the point 2/3. Most of the time, though, we are going to be dealing with uniform density. Both because it's easier to deal with those types of problems, but more so because most of the materials that we would choose to use in terms of engineering are going to be of uniform density. So if we think about that, and we're thinking about something in sort of 3 dimensions, so imagine this is some 3-dimensional shape, if you can imagine that, some 3-dimensional shape there. The x center of mass would equal 1 over m times x dm. And this is nothing new to us. But what we need to know now is the idea that, let's just say that this is some known density, where our density is m over v. We can do some replacements here so that we could think about, well, that our density is the same as dm over dv, since we're talking about uniform density here. So dm would be our density times dv. And similarly, going back up to this first equation, we could rewrite m as density times v. So therefore, we can get our center of mass written in terms of how its volume changes. So we could say that our x center of mass equals 1 over mass, where mass is density times v, or rho v, times the integral of x dm, where dm is rho dv. Well, we see very quickly densities cancel off, and what we get is that the x center of mass is 1 over the total volume times the integral of x times dv. And we'll look at examples of these problems later on. But by the same sort of construction, we would get that the y center of mass is 1 over volume y dv, and the z center of mass is 1 over volume times z dv. So these are a helpful way for us to think about uniform density in terms of how an object's volume is changing. However, frequently, most often, we can be clever in our solution. So let's look at one more challenging problem. While those equations that we learned can be obviously really helpful, it's easiest if we can identify shapes as points. And when we talk about using them as points, we're talking about at their center of mass. And this is most easy when we're dealing with problems that are uniform density. So to look at an example of this, imagine we've got some circle. And what we're going to do, and it's got some mass m and radius 2r, is we're going to remove a circle right that's symmetric about the x-axis. And so clearly it would have a radius of r. So we're just going to remove that circle from it. And what we want to do is find the new center of mass. Well, we know that the original center of mass would have been right here at the middle. And the center of mass of my circle that I'm removing is going to be right at this distance, r from the old center. So that's my center of mass of the object I removed. And then my new center of mass, it was here. Now it's going to slide a little bit over to the left. And it's sliding a little bit over to the left because I'm removing the same amount of circle from above and below the x-axis, so it won't affect my y position. But since I'm removing mass from the right-hand side, I have more mass on the left-hand side, so it's going to shift to the left. So let's define some things. Let's call say A equals not the mass, but the circle, the big circle with chunk removed. And B equals the little circle that was removed. and C equals the original circle. So what we could do is we could think about saying, well, if I took the big circle with the chunk removed and added it to the little bit of circle removed and just filled the hole, what I would get back is the original circle. Right? Similarly, if I added the center of masses of A and B, I should get back the center of mass of C. So what we could do is we can treat these two shapes, A and B, as points. So we've got one point here, and we'll call that A, and another point here, and we'll call that point B. And we're going to add them together to find their combined center of mass. And their combined center of mass is going to be the center of mass of the circle. Okay, so if we call this the origin A, and we're going to define x to be the distance that we've shifted the center of mass from the original point in the center of the circle, then here is going to be my center of mass, some distance x. And from A to B, we're going x plus r. So the center of mass of A and B being added together, the center of mass must equal x, where we're calling the origin at A, because the center of mass would be a distance of x from the center of mass of A. And the way that we calculate that center of mass is the mass of A times the distance it is away. So, So times 0 plus the mass of B times x plus r all over the total mass. Well, this is just going to go to 0, so we need to evaluate this little chunk. And to find the mass of B, well, let's do that work up here. To find the mass of B, what we know is that the density of the whole circle is going to be its total mass over its area, which is pi times 2r squared. So to find the mass of B, what I'm going to do is I'm just going to multiply the area of B to the area of B, which is pi r squared, times the density, m over pi times 4r squared. And that's going to get me the mass of B. Which is m over 4. So what we get is x equals m over 4 times x plus r over m. M's cancel out. Do a little algebra, and we get that 4x equals x plus r, or x equals r over 3. And there is our new center of mass. So it's shifted a distance of r over 3 to the left of its original position.